Today's topic we will study and discuss about linear time invariant systems and convolution, which is chapter 2 for ECEN220 class. Okay, as you remember, this is actually the outline representation of continuous time signals using unit impulse response of continuous time LTI systems and continuous time convolution, properties of convolution, the unit impulse and other singularity functions and differential equations. Okay, as you remember in the previous chapter, we studied about linearity and time invariant properties. These two properties are very important because many physical processes possess linearity and time invariance properties, and they can be modeled as linear time invariant systems. And especially the property of linearities and time invariance is very important to compute the output of a system given a certain input. If we have an input which is a sum of a set of basic signals, then we can find the output due to the individual basic signals, and the complete output for that input will be the sum of the outputs of the basic signals. This is called superposition property, which is very important. And another one is signals can be represented as a combination of delayed impulses. This is very useful property because for an impulse we have an output called the impulse response or the unit impulse response. And if we can express the input signal as a linear combination of delayed impulses, then the corresponding output signal will be the linear combination of the delayed impulse responses. Okay, so this is very important to compute the output of any signal, the output to any input for a certain system. Okay, to start with, if we have any continuous time signal, we can approximate it using a staircase function. Here, for example, this signal is continuous in time. For the duration 0 to delta, I can approximate it as a constant value, which is x of k delta. For the duration k delta less than tk plus 1 delta. Okay. So if you do this, you will have a lot of staircase function, staircase approximation. That means, okay, like this. It's like which is used in the integration, in the concept of integration in calculus. Okay, so you approximate the continuous time signal by these pulses, delayed pulses actually. The sum of delayed pulses. So if, for example, if we define Dirac delta t, which is equal to, which has an amplitude 1 over delta between 0 and delta, delta is a very small time, then I can write the value of the signal at any time, which is k times delta, the value of the signal x at k times delta, which is constant between k delta and k plus 1 delta, this pulse function is equal to x k delta Dirac delta t minus k delta times delta. Why we multiply by delta? Because this has an amplitude 1 over delta. If we multiply by delta, then it will be 1. So 1 times the value at k delta, it will be x of k delta. So overall, the signal, the previous continuous time signal, can be approximated using this summation approximation from k minus infinity to infinity x of k delta times Dirac delta t minus k delta delayed impulse, which is the delayed pulse, this signal, multiplied by delta, the time step delta. Now, as we reduce delta in the limit when delta goes to 0, what will happen? This summation will change to integration from calculus. Remember the concept of integration. So this summation will change to integration. This x k delta will become x at any time tau, and this one Dirac t minus k delta Dirac t minus tau, and this k times delta will become tau now, and delta will become d tau. So I expressed x of t, the signal, the input signal, is equal to integration from minus infinity to infinity x tau Dirac t minus tau d tau. Okay, we are in the tau axis now. Okay, we are integrating with our variable of integration is tau. That's why we have d tau. And we have Dirac t minus tau, which is defined at t is equal to tau. So this property, we call it shifting property of the unit impulse. So the input signal is the integration of x tau Dirac t minus tau d tau. So we represented the input signal as a function of the impulse function, that means. Okay, so if we do so, if you remember Dirac t, what's Dirac t? Dirac t is a function which is introduced by Paul Dirac in the 1920s. So in chapter 1, if you remember, how do we define it? Dirac t is equal to 0 for t different from 0 is equal to infinity at t is equal to 0. The integration of Dirac t a little bit to the right of 0 and to the left of 0, the limits are to the right of 0, 0 plus, to the left of 0, 0 minus. Dirac t dt is equal to 1. So the integration result is 1 because of this. If you find the area of this rectangular pulse having an amplitude 1 over delta and duration delta, of course the area of this will be 1, or the integration from minus infinity to infinity will be 1. But as delta goes to 0, 1 over delta will become infinity. That's why the impulse is defined infinity at t equal to 0. But the integration result is equal to 1. Okay, so now let's have this system, a continuous time system. And the system is like this is a block now. I represent it with a certain block. It has an input x of t and an output yt. If I give an input Dirac t, what is Dirac t? The that we defined here. Okay, Dirac t defined as this, the impulse function. Then the output is h of t. We call h of t the impulse response. Why we call it impulse response? Because the input is impulse and we are expecting a response for that impulse. So we say it impulse response. Okay, so we denote it with a letter h, small h, and we call it h of t. So if the input is Dirac t, the output is h of t, and we call h of t the impulse response. Now, if this system is linear and time invariant, if I give Dirac t minus tau, that means a delayed impulse, then the output will also be delayed by the same amount using the time invariance property. So it will be ht minus tau. Okay? So we can combine now the linearity and the time invariance property. If I multiply by x tau. If I give x tau dirac t minus tau, then the output will be x tau ht minus tau, okay, due to the scaling property of linearity, okay, x tau ht minus tau. So if the input is x tau dirac t minus tau, the output is x tau ht minus tau. Again, due to linearity, if I do integration for the input, the output will have the same integration, okay. So for the input x of t, which is represented by this, mathematically represented by this, the output is from infinity to infinity x tau ht minus tau d tau. What is the difference between the input equation and the output? In the input equation, I have impulse, dirac t minus tau. In the output equation, I have the impulse response, ht minus tau d tau. Okay? This overall integration, we call it convolution integral. And we write it x of t, this star sign, x of t convolved with h of t. Okay, x of t convolved with h of t is this mathematical expression. Okay. Now, what is the process when we are doing, when you see this integration, it looks simple, but there is some process when we are doing the integration. Why? Because we are integrating with respect to tau. The integration variable is d tau. And the final result is y as a function of t, y of t. Okay? So what are the steps? First, we change x of t and h of t to x tau and h tau. This is very easy. We just replace the time t by tau. So your x-axis, if your x-axis is t, variable t, then you will make the x-axis variable tau. So after h tau, you flip h tau and you get h minus tau. Okay, how you get it? You flip it. That means you make your y-axis as a mirror and you swap the left and the right side. Okay, the right side goes to the left to the right. And after that, there is time shifting by t. Okay, now t is constant. Why? Because our integration variable is tau, d tau, tau. So the sliding, so ht minus tau. Now when we slide the flipped signal, if t is positive, we shift it right. If t is negative, we shift it left. Okay? Because we have a first flip, that's why. In chapter 1, if you remember, when beta is negative, shift right, beta positive, shift left, because there is no flip here, because we did flip first. Then when t is positive, then shift right. When t is negative, shift left. Then after that, we multiply x tau times ht minus tau. Then we integrate. The final result is the final step is integration. Okay. So this is a convolution integral or superposition integral also we call it. Okay, now we do some examples. Let's go to the additional class notes, lecture notes. Okay, this is all we discussed already. If I have h of t now, we discussed about the impulse. Okay, so in general here, if I have Dirac t input, h of t is the output, Dirac t minus tau, input, ht minus tau, output. If I multiply by a times Dirac t minus tau, the output will be a times ht minus tau. If I multiply by x tau Dirac t minus tau, it will be x tau ht minus tau. Then if I integrate, which will give me the input signal x of t, left side and right side, I have the integration of this one, which will give me the output, and which we call it convolution integral. Okay, so already we said the steps x of t, h of t, we change it to x tau, h tau. Then h tau, we flip it to get h minus tau. Then we shift it to get ht minus tau. Actually, ht minus tau means h of minus tau plus t. Okay? So if t is positive, shift right. Why? Because we have flip here. If there was no flip here, minus. If t is positive, shift left. If t is negative, shift right. If there is no minus tau, but I have minus tau the flip, then it will be exchanged. That's why. So and then after that you multiply and then you do integration. Okay, let's start with example. The first example is the example. Let h of t is Dirac t, the impulse itself, and I have an input x of t, any input, and I have a system which is Dirac t. What will be yt? We follow the steps. Yt x of t convolved with h of t from minus infinity to infinity. X tau ht minus tau d tau. Tau ht minus tau will be Dirac t minus tau d tau. But what is Dirac t minus tau d tau? It will be 1, it will be infinity at t is equal to tau. 0 otherwise. So this multiplication will be 0 except at t is equal to tau. Then at t is equal to tau, x tau is in fact x of t. Okay, then x of t will come out of the integration. Then it will be the integration minus infinity to infinity of Dirac t minus tau, but the integration of the impulse is 1. Then finally we get the result x of t. Okay, that's why. Okay, if I go back here, here is x tau, any function here, x tau. Then when I multiplied with an impulse which is at t, at tau is equal to t. So when you do the multiplication, all the multiplication result will be 0 except at t, at tau is equal to t, where x tau is equal to x of t. So it will be x of t, then x of t will come out of integration. Then the integration of this impulse is equal to 1. Then it will give me x of t. So x of t is equal to x of t. Okay, so the shifting property that we discussed, right? So this is first example. And if I delay it, what about if I have a system, a delay system, we call it h of t Dirac t minus t naught. Now the impulse is at t naught, right? At t naught, what will happen? Then again, when we apply the formula x of t, x tau, ht minus tau d tau, integration. Okay, ht minus tau means Dirac t minus t naught minus tau. But this one has value at t at tau is equal to t minus t naught. Okay, at tau is equal to t minus t naught, it is infinity. All other places it is 0. So at tau is equal to t minus t naught, x tau will have x of t minus t naught. Okay, then it will come out of integration because it will be independent of tau. Then the result will be xt minus tau, xt minus t naught. Okay, so you see here, Dirac t minus t naught minus tau is equal to infinity at tau is equal to t minus t naught is equal to 0 otherwise. All right, then this will be x of t minus t naught and the integration of the impulse. The integration of the impulse is equal to 1. So 1 times xt minus t naught, xt minus naught. So y of t is xt minus t naught. Okay, so a delayed input. If I have a delayed system, I will get a delayed output. That means. Okay. Now another example. Another example is here. If I have u of t is equal to this is unit step, u of t is equal to 1 for t greater than 0, 0 for t less than 0. And remember, unit step function is the integration of unit impulse function. And for t less than 0, this integration will be 0 because the impulse is at tau is equal to 0 and 40 greater than 0, this is equal to 1. This is actually a proof why unit step is equal to 1, 40 greater than 0, and 0, 40 less than 0, because unit step is given by from infinity to t Dirac tau d tau, or the derivative of unit step function is unit impulse function. Okay, now let's have a system with h of t is equal to ut. Ut is the unit step function. And I have n input x of t. What will be the output y of t? Okay, we follow again the convolution steps. Y of t is x of t convolved with h of t from minus infinity to infinity x tau ht minus tau d tau. The first step is change x of t and h of t to h tau, x tau. So h tau will be u tau. U tau will be unit step function starting from 0. Your axis will be now tau. Okay, so it will be 1 for tau greater than 0. This is h tau. U minus tau, h minus tau is u minus tau. So flip it. You flip it. So it will be 1 from minus infinity to 0 and 0 40 greater than 0 because we flip it. Remember, we swap the right to left, left to right. Okay. So ht minus tau, and then we get ht minus tau. Shift it. Okay. If t is positive, shift right. If t negative, shift left. So let's say now we arbitrarily take t positive and we shift it right. So that means the flipped signal, this one, will shift by right. So every point in time will be shifted by t. So the 0 point here will go to t, that means. Okay, so the 0 point will go to t. So that means ht minus tau, which is ut minus tau, will be 1 from minus infinity until the point t. Okay, of course, for tau greater than t, it will be 0. Okay, this is ht minus tau, which is ut minus tau. All right, now let me have any signal x tau. If I multiply any signal x tau with this function, okay, this function has value 1 from minus infinity until t. It is 0 for tau greater than t. So what will happen if I multiply by any signal x tau? It will give me the same signal x tau from minus infinity until t. 0 otherwise. Okay, why? Because after tau greater than t, it is 0. So 0 times x tau will be 0. So basically, the integration will change from minus infinity to t, x tau d tau. This thing, ut minus tau, we can remove it. Why? Because its function is only to get the interval of integration. Otherwise, its value is equal to 1. Its amplitude is 1. So 1 times x tau will be 1. Okay? So it will be from minus infinity to t x tau d tau. So what happened is very nice result we get. If the system response, the system impulse response is unit step function ut, then the output y of t is the integration of the input. That is, y of t is infinity until tx of tau d tau. So this system, we call it integrator system. Okay, so the integrator system, of course, will give me at the output the integration of the input from minus infinity to t, and the integrator is characterized by h of t is equal to ut, unit step function. All right, now if I change, okay, if I what about if I do another example here? If I say x of t is equal to ut and h of t, what should I get here? Okay, what should I get? Let's see. Let's continue this. X of t is equal to ut, and and I have h of t, any system h of t. Okay, again using convolution y of t, x of t convolved with h of t from minus infinity x tau ht minus tau d tau. Okay, convolution is commutative. That means like normal algebra, arithmetic algebra, a plus b is equal to b plus a, and a times b is equal to b times a. Like that, y of t, x of t convolved with h of t is the same as h of t convolved with x of t. Okay, because now here x of t is given, that's why I make it here commutative. So it will be ht convolved with x of t, which is from minus infinity to infinity h tau xt minus tau d tau. So the role of x and h will be changed here. Okay, here ht minus tau, here xt minus tau, and here x tau, here h tau. Okay, you'll get the same result. And this commutative property is useful because sometimes it is easy to do the convolution using this instead of this. Okay, instead of this one. Instead of doing this integration, it may be easy to do this way. That's why the commutative property is very nice. So in this case now, from minus infinity to infinity, h tau xt minus tau d tau. But what is xt? Xt is ut. So xt minus tau means ut minus tau d tau. So what is ut minus tau d tau? The same thing, the same graph. This is ut minus tau d tau. Ut minus tau, t minus tau means it is 1 from minus infinity until t, and 0 for tau greater than t. Therefore, here the role of the ut minus tau will be again to adjust the interval of integration. It will be from minus infinity until t of h tau d tau. You see the difference now? So if the input is unit step, the output is the integration of the system impulse response from minus infinity to t h tau d tau. Which means if I give a unit step input, okay, if I give a unit step input to the system, then the output will be the integration of the system impulse response. In other words, if I after I find the output, if I find the derivative of the output, then I will get the impulse response. Okay, so to get the impulse response, another way is you give a unit step input. By giving a unit step input, you will get the output yt, which is the integration of the impulse response. Then the derivative of the integration of the impulse response will give me the impulse response, because the derivative will cancel the integration and I will get the impulse response. So this is actually a way, some experimental way of to get the impulse response. You just give the unit step function and get the output of that system, and then you differentiate the output and you will get the impulse response. Okay, so because u of t is the integration of the unit impulse function, then s of t, the step response of the system, will be the integration of the impulse response. Okay, the step response means the response of the system when I give a unit step input, and it will be the integration of the impulse response, because the unit step function is the integration of the unit impulse function. The step response of the system is the integration of the impulse response of the system. Okay, and here is an alternative way to check this, to prove that, and you can follow. And if you don't understand, you can always ask me. You can check this also, alternative way. Okay, now let's go to another example. Let me have x of t is equal to e to the power of at ut. where a is greater than 0. If a is greater than 0, remember in chapter 1 what we have? We have exponentially decaying function. Of course, the function starts from t equal to 0 because of unit step. This means when we say this e to the power of at ut, it means multiplication of e to the power of at times ut. But ut starts from 0. Starting from 0, it is 1. Before 0, it is 0. And the result of x will be 0. X of t will be 0. But for t greater than 0, ut is 1. So 1 times e to the power of at, it will give me e to the power of at. So the graph of x tau, okay, remember how to get x tau? We change t to tau. The graph of x tau is x tau e to the power of minus a tau u tau is like this, exponentially decaying function starting from 0, 1 at 0, 1 and decaying. And for tau less than 0, it will be 0 because of u tau. U tau is equal to 0 for tau less than 0. And h of t, ut, and u tau is this one. Starting from 0, it is 1. Okay? Then what is the next step? We flip h tau. We flip and we get h minus tau. H minus tau means flip this function, this one. When we flip, it will be from minus infinity to 0, it will be 1. And for tau greater than 0, it will be 0. Okay? After we flip, we slide, we shift. Okay, now we have two options. Here, by comparing x tau and h minus tau, we can do the shifting, okay? One shifting is for t less than 0. For t less than 0, okay? H t minus tau, which is ut minus tau, will be 1 from minus infinity until t for t less than 0. And it will be 0 for tau greater than t. Okay, this is the shift result for t less than 0. Remember, for t less than 0, shift left after flip. All right. So after that, after flip, we multiply. Okay, we multiply x tau and ht minus tau. This one and this one. Okay, this is case 1. When you multiply these two, the result is 0. Why? Because for tau less than 0, x tau is 0. I don't have anything here. For tau less than 0, this one has something in this region. So because x tau is 0, the result will be 0. So the product is 0, means y of t is 0. Okay? For t, what about for t greater than 0? For t greater than 0, the shift, okay, after flip, this is a flip. After flip, the shifted result is this. For t greater than 0, this is u of t minus tau, which is ht minus tau, u of t minus tau for t greater than 0. It will be from minus infinity to t. So when I multiply with x tau is this function. Now graphically multiply the two functions. For tau less than 0, the result will be 0. Even though I have 1 here, the result is 0. For tau between 0 and t, this is 1, and this is exponentially decaying. So it will give me the exponentially decaying function. And for tau greater than t, this is 0, this is something, but 0 times something will be 0. So what will happen? Only the product will be non-zero between 0 and t. Between 0 and t, I will have exponentially decaying function. Okay, as seen from here, I will have this x tau ht minus tau will be decaying function from 0 to t. So the interval of integration will become from 0 to t e to the power of minus a tau d tau. We remove these two. These two, they helped us to get the interval of the integration. The interval of integration between 0 and t. Okay, then the integration of this will be from the integration rule, negative 1 over a e to the power of minus a tau. Evaluate from tau is equal to t to 0, then this will be e to the power of minus at minus e to the power of 0. E to the power of 0 is 1. Then I have minus here. And finally, the result will be 1 over a times 1 minus e to the power of at. So the final output is y of t is equal to 0 for t less than 0. Y of t is equal to 1 over a times 1 minus e to the power of at for t greater than or equal to 0. And the final step is plotting. When we plot this, okay, this one is exponentially decaying, as we saw earlier, and 1 minus this will be exponentially growing function. So in fact, y of t will be a growing function starting from 0. In the limit, when t goes to infinity, so this will be e to the power of negative infinity. E to the power of negative infinity is 0. So 1 minus 0, 1, it will be 1 over a. So in the limit when t goes to infinity, it will be 1 over a. So this will be the result of the output. A is for any a greater than 0. So if a is 2, it will be 1 over 2 here. If a is 3, 1 over 3, and so on. Okay, this is how we do the integration as a convolution. Okay, another example. Let me have x of t e to the power of 2t u minus t, okay, and h of t u t minus 3, okay. And that means, again, the first step, x of t change to x tau. Now, because of u minus t, what is u minus t? It is 1 from minus infinity to 0, and 0 for t greater than 0. So this u minus t, it helps us to limit the interval of this exponential. Okay, so the interval, this exponentially function will be from minus infinity to 0. For t greater than for tau greater than 0, it will be 0 because of u minus tau. Okay, so this is x tau decaying to the left. Okay, growing to the right. Okay, so this is x tau. And what about h tau? H tau is u tau minus 3. U tau minus 3 means shift of unit step by 3 to the right. So it starts from 3 and goes to infinity. So for for tau greater than 3, it is 1. For tau less than 3, it is 0. This is h tau u tau minus 3. After this step, we have the flip step. Flip it. When you flip, you have u minus tau minus 3, which is from minus infinity to minus 3, it is 1, and 0 for tau greater than minus 3. Okay, so it will be from minus infinity to minus 3. Then we have the shift. We shift it. We shift it by t means every time step will move by t. So this minus 3 will be, this point will be t minus 3. Okay, so we add t here. So it will be t minus 3. So u of t minus tau minus 3 will be this one, right? Okay. Now we compare x tau with ht minus tau. We compare these two, okay? And we make the product and we compare the two by comparing the two. We make the product. So when tau t minus 3, okay, is less than 0, the product of these two functions will be from minus infinity until t minus 3, somewhere here, until t minus 3, okay? Okay, because t minus 3 is less than 0. And because this is 1, it will not change the amplitude of x tau. What happened? Only it makes x tau from minus infinity until t minus 3. So the first case is t minus 3 less than 0 means t less than 3. Then the integration will be from minus infinity until t minus 3 e to the power of 2 tau, and we remove u tau and ut minus tau minus 3 because they are 1. So it will be from minus infinity to t minus 3 e to the power of 2 tau d tau, which is equal to 1 over 2 e to the power of 2 tau from t minus 3 to tau minus infinity. So it will be e to the power of 2t minus 3 e to the power of minus infinity. What is e to the power of minus infinity? This is 0. So the result will be half e to the power of 2t minus 3. Okay, this is for t less than 3. Okay, what about t minus 3 greater than or equal to 0? Okay, let's go again here. That means this point, from ht minus tau graph, this point is here. Okay, t minus 3 greater than 0 means it is here. So what will happen? The product of this x tau times ht minus tau, it will be x tau from minus infinity to 0, 0 otherwise, because whatever this guy after 0, no change for the product, because the product only until 0. Okay, so because this is if it is any value after 0 to the right, because this is 0, the result will be 0. So the product of the two will be from minus infinity until 0. So the integration interval will become from minus infinity until 0 e to the power of 2 tau. And this integration will be 1 over 2 e to the power of 2 tau. And between tau 0 and tau minus infinity. And this will be e to the power of 0, e to the power of minus infinity. E to the power of minus infinity is 0. So this will be half. Now we summarize the result. Y of t will be half e to the power of 2t minus 3 for tau for t less than 3, and 1 over 2 for t greater than or equal to 3. So graphically, it's like this. It is growing exponential function. So it stops at 3. At 3, the value is t is equal to 3, 3 minus 3, 0. E power of 0 is half. Also here also half. So after that, it's constant half. Okay, this is the output. Okay, that's all about convolution examples. I hope you understand. And some more examples I have also here in the lecture slides. Please follow this one. I have another example. This follows this convolution example. Okay, so try to look again the examples and redo by yourself the examples, and remember to summarize the steps of convolution. First, we change xt to and ht to x tau and h tau. Second, we flip h tau to get h minus tau. Next, we shift h minus tau to get ht minus tau. Then we multiply x tau times ht minus tau. Then we do the integration, of course, using different cases. The cases, we construct the cases based on the relation between x tau and ht minus tau. We look the two graphs, and we by looking the two graphs, we decide the cases. The cases can be 2, can be 3, or more than 3, depending on the graph of x tau and ht minus tau. Okay. Thank you very much for listening to this lecture, and see you in the next lecture video.